All right, so let's get started. We're going to continue on chapter 19 here, our discussion of thermodynamics. Last time we worked to build this equation here for our chemical potential. We have our delta G, our free energy, is equal to the enthalpy times minus temperature times delta S, which is our entropy. All right, so again, delta G we call the free energy. This tells us whether or not a reaction is spontaneous, right? Whether or not it will occur spontaneously. Delta G is less than 0, that's a spontaneous reaction. If delta G is greater than 0, that's a non-spontaneous reaction. Delta H was the enthalpy. This tells you about whether heat is released or absorbed in a reaction. All right, T is just temperature. Importantly, we can just make note in thermodynamics, it's very important that you always use your temperature in units of Kelvin. All right, and delta S is again this very weird quantity here, entropy, which tells you whether your reaction has created more order or more disorder. And so again, delta G is the one that will tell you whether or not your reaction occurs. If it's negative, that's a spontaneous reaction. If it's positive, that's a non-spontaneous reaction. And we got these two components. The heat component, our enthalpy, and then that disorder component, our entropy. All right? And we talked about a few specific reactions. The melting of ice, for example. We know, we've seen this happen, right? This is a reaction that will occur spontaneously. All right, it's entropically favorable because you're creating a more disordered state, but it's an endothermic reaction, right? So again, we got this push-pull going on between our entropy and our enthalpy. And on the flip side, we saw the exact opposite, talking about these precipitation reactions that you did in lab. This was another reaction that you saw occur in front of your eyes, right? It's a spontaneous reaction. This one would be entropically unfavorable because you're creating that ordered solid, right? So then why is it still allowed to occur? Because it's an exothermic reaction, because there's a release of heat, right? So what we're going to see is between these two components, as long as one of them is favorable, the reaction can still be spontaneous. All right, so we're going to take a little bit of a deeper dive using this equation. Let's just copy this onto a new page. All right, and we're going to make, a little bit of a cheat sheet table here. Looking at the value of each of these three components. Right, so what do I mean by that? Well, let's say that we have an exothermic reaction that is entropically favorable. All right, if it's an exothermic reaction, what is the sign of delta H? Positive or negative? So for an exothermic reaction, we have a negative delta H. And a reaction that is entropically favorable is a positive delta S. So if we look at our equation here and we just think, what's going to happen if I plug in a negative value for delta H? and then I take a positive value for delta S, but then I multiply it by negative T, right? What's a positive times a negative? That's going to be a negative value. And if I take two negative values and add them up, I'm always going to get a negative sum here, right? So this would be a reaction that would be spontaneous, okay, under all temperatures. All right, so if something is both exothermic and entropically favorable, from the universe's standpoint, that is best case scenario, right? Not only is it releasing, dissipating energy in the form of heat, it's also creating a more disordered state, right? So boom, universe is super pumped about that. Always gonna let that type of reaction occur. All right, and then let's look at the flip side here. What if instead we have an endothermic reaction? That is entropically unfavorable. Okay, well, an endothermic reaction would have a positive enthalpy, right? And being entropically unfavorable means a negative entropy. All right, so again, let's go back to our equation here and plug this in. If I have a positive value for an enthalpy, and then negative T times a negative value, what's a negative times a negative? Positive. And if I add up two positive numbers, I'm always going to get a positive delta G, right? So this would be an example of a reaction that would be non-spontaneous at all temperatures, right? A positive delta G. All right, this is an energetic loser from the universe's standpoint. It's not releasing any energy in the form of heat, it's actually absorbing energy, and it's not creating a more disordered state, it's creating a more ordered state. Universe doesn't like it, will never allow something like this to occur. Okay? All right, but now let's mix it up here. We're gonna see a conflict between our entropy and enthalpy terms. So let's look at a reaction that from an enthalpy standpoint is favorable, an exothermic reaction, but from an entropy standpoint is unfavorable. All right, so I have an exothermic reaction, a negative delta H, but then an entropically unfavorable reaction, so a negative enthalpy, or entropy, I'm sorry. Okay, so let's plug these back into our equation here. Again, we have a negative enthalpy, and then minus T times a negative number. All right, so now this component here is going to be positive. So if I have a negative number plus a positive number, what's going to be the sign of that delta G? Well, it depends on just what those values are, right? I got like this conflict going on. If the negative number is bigger, then it's going to be a negative delta G. If the positive number is bigger, it's going to be a positive delta G, right? So it's going to depend on the value here. But what's important is that this term here depends on that temperature, right? So this term right here, this becomes larger as temperature increases. So whether or not this reaction is spontaneous is going to depend on what that temperature value is. All right? So let's see if we can't predict this. Let's plug in the absolute lowest temperature that we can possibly think of in Kelvin, which is absolute 0. All right? So if I make my temperature here 0, what's going to be the sign of delta G? Positive or negative? All right? In that case, this entropy component is nothing, doesn't matter at all. And so my reaction overall would be negative, which would be spontaneous. Okay? So this would be a reaction that is spontaneous at low temperatures. Right? A negative delta G at low temperatures. But as my temperature increases and increases and increases, and this positive component becomes greater and greater and greater, it'll eventually sort of dominate this equation here, and my overall delta G will be positive. So this would be a reaction that is spontaneous at low temperatures, but at high temperatures is non-spontaneous. All right, and then lastly, we can look at the flip side here. What if we have an endothermic reaction? All right, the universe doesn't really like endothermic reactions, but it is entropically favorable. All right, again, plugging this into our equation here. We have a positive enthalpy minus T times a positive entropy. So now this component here together is going to be negative. All right, so I have a positive plus a negative. What's going to be the value of my delta G? Again, it's going to depend on the actual value of those two components. In this case, let's again think of what's going to happen when we plug in our absolute lowest temperature, absolute 0. Is this reaction going to be spontaneous or non-spontaneous at those low temperatures? Non-spontaneous, right? This term will drop out and my delta G is positive. So at low temperatures, this reaction is non-spontaneous. Delta G is positive. But once I increase my temperature high enough, that entropy term will dominate and this reaction will become spontaneous. All right, so again, we have these two components to whether or not a reaction will occur. The enthalpy component and the entropy component. If both of these are favorable, we got an exothermic reaction that is entropically favorable, great. The universe will let that happen regardless of temperature. If it's the opposite, if it's unfavorable in both capacities, then it's not going to let it happen at all. It's always going to be non-spontaneous. But we can have this kind of push-pull conflict between these two terms, where one of them's favorable and the other one's unfavorable, and then it's going to depend on temperature. Okay? And we've seen two examples of this already where we have this conflict, things that we kind of know intuitively. All right? An example of an entropically unfavorable event that is exothermic would be freezing. Going from a liquid to a solid. This is a process that would create more order, but is exothermic. There's going to be a release of heat in order for these liquid water molecules to form solid water molecules. okay? And this is a reaction that we know occurs spontaneously at low temperatures, right? Inside your freezer, ice will spontaneously freeze, or water will spontaneously freeze, all right? But does not occur at high temperatures spontaneously, okay? So then the flip side, an endothermic process that is entropically favorable would be something like boiling of water. If we take liquid water and we heat it up, we spontaneously form gaseous water. That is a process that is entropically favorable, where you're creating a more disordered state, but it's endothermic. Those water molecules have to absorb heat in order to get into the gas phase, right? So again, we know that this is a process that will spontaneously occur at high temperatures, but we're not worried about our water bottles all of a sudden like erupting into steam, right? So only occurs at high temperatures. Cool. All right. So, talking more about these thermodynamic quantities here. Delta G, delta H, and delta S. These are very useful quantities because they are what are called state functions. All right, a state function means that its value is path independent. All right, so let me explain what the heck this means. Using an analogy here, it's a little bit harder to see for these particular thermodynamic quantities. All right, but let's draw a little picture here. This is my beautiful rendition of a mountain. Okay, and we got two hikers. The blue hiker and the red hiker. And they are both gonna start at that same location. Okay, same point on our trailhead here. All right, our blue hiker is Mr. Fitness. He just beelines it right up the side of the mountain to get to the very top there. Not worried about the incline, just powers through it. All right, our red hiker, not into it. It's gonna take the switchback route. Back and forth and back and forth and back and forth in order to get to the top of the mountain. Okay, so distance is what's called a path function. Its value depends on the path chosen. All right, so which hiker hiked the greatest distance? It's going to be the red hiker, because it took that long meandering trip up the mountain, right? Back and forth and back and forth. Simply covered more ground. So red hiked the greatest distance. All right, but there is a very similar quantity called displacement. And displacement is what we would call a state function. Its value is independent of the path chosen. All right, so displacement is literally just the difference between where you started and where you ended. Both hikers started at the same place. Both hikers ended at the same place. So even though the red hiker traveled the greatest distance, red and blue have the same displacement. right? And again, our thermodynamic quantities, delta G, delta H, and delta S, these are state functions, much like displacement. It doesn't matter how you got there. All that matters is where you started and where you ended, okay? From a chemical reaction standpoint, like how does that translate into chemical reactions? What that means is that if you calculate one of these quantities, like the free energy, for a reaction that takes place in one step, you would get the exact same value as if this reaction took place in 20 different steps, okay? All that matters is where you started and where you finished. And this is gonna make these quantities very, very useful, all right? So let's see why that is. Let's say that I'm in the lab and I'm studying reactions here, all right? So I'm gonna study two different reactions. All right, I like working with nitrogen and oxygen. So in my first reaction, I'm going to combine nitrogen with oxygen gas. This will produce two nitrogen dioxides, dinitrogen monoxides rather. All right, and I've studied this reaction. I know the delta G for this reaction. I did my thermodynamic measurements here to get my delta G. All right, and I know this other reaction, where if I start with that dinitrogen monoxide, I can do a combination reaction to get this tetranitrogen dioxide. I know the delta G of that reaction, right? Again, I studied these reactions, I did my measurements here, so I know what the delta G of each of these two reactions are. Okay? Well, now what we're going to do is we're going to sum these two reactions up. So what I mean by that is all of my reactants, I'm going to add up on my reactant side. So my two nitrogens, my oxygen, and those two N2Os. And I'm going to do the same thing on my product side. I have my two N2Os and my N4O2. So now what we're going to do is we're going to cancel everything that appears on both sides of our chemical equation. If we got an exact match on both sides, we're going to cancel it out. Anybody see anything that I can cancel here? That N2O, right? Boom. So my net reaction here are these two nitrogens plus an oxygen to give us N4O2. And this is a new reaction. I've never studied this one, don't know her, all right? But I have studied these two independent reactions, and the sum is this third reaction. So the delta G is just going to simply be equal to the sum of my delta G for those two reactions, right? Because it doesn't matter what path I take. It doesn't matter if I do this reaction in one shot or if I do it in these two steps here, my delta G is always going to be the same, okay? So our delta G's are just simply additive here, since all I had to do was sum these two reactions in order to get my new reaction here. All right, so when scientists realized that, they realized that they had a very powerful tool on their hands. One way to be able to predict what our delta G is, whether or not reactions happen, given just a small set of known stuff. Like if we know the delta G's for a few different reactions, we can use those to get to any reaction. And so what they did was created our constants page for this particular chapter, this massive list All right, we got a big constants page for this chapter here. And just to point out what this is, for any compound that you can find on this list, it gives you a delta H, a delta G, and an entropy for that compound. Okay, so let's just take this example here. So let's say that I want to know whether sodium will combine with fluorine gas to spontaneously produce solid sodium fluoride. I want to know the thermodynamics of this reaction here. Is this reaction spontaneous or non-spontaneous? All right, first things first, we got to balance this chemical equation. So everybody take a second to balance your chemical equation. And then what we're going to do is we're going to go to our constants page and we're going to look up each of these compounds on our table. All right, so I'm just going to copy and paste here. All right, so here is our sodium fluoride values. Whoa. Sodium, so now I need to grab, and I'm paying attention to the states here. I started out with solid sodium, so that's what I'm going to use. All right, and now I just need my fluorine gas. A, B, C, D, E, F, G. Cool. So that's that value there. Cool. All right, so all I did was go to my table and grab those three components. Let me get rid of this so it's a little bit clearer. All right, we have our solid sodium, that's one of our reactants. We have our fluorine gas, that's our other reactant. And then we have our product, the sodium fluoride. All right, and to be clear, if we look at our headers here, this first column is your delta H, the second column is the delta G, and the third column is the entropy. Okay, so we can use these values. We're going to focus on delta G. We want to know whether or not this reaction occurs. Okay, so in order to get our delta G for our reaction, when we build our equilibrium constants, it's products over reactants, right? That's what we chant to ourselves when we build our equilibrium constants. When we do our thermodynamic variables here, it's going to be products minus reactants, all right? So what I'm going to do is I'm going to take the sum of all of my products times their stoichiometric coefficients, and I'm going to subtract the sum of my reactants times their stoichiometric coefficients. All right, so I'm going to look here. My product is this negative 546.3. I need to multiply that by that stoichiometric coefficient of 2. So 2 times negative 546.3. And then I'm going to subtract the sum of my reactants. Okay? It's going to be important that you put that in parentheses so that that minus sign gets distributed. All right, so in this case, sodium also has a coefficient of 2, but its delta G is 0 here, so 2 times 0 plus fluorine, which is 0. All right, so I'm really just subtracting 0. And so I get a delta G for my reaction of negative 1092.6. Okay, let's be good here. Our units for delta G are kilojoules per mole. All right, so if a mole of this reaction happened, this would be my free energy here. So is this reaction spontaneous or non-spontaneous? This would be a very spontaneous reaction. That is a huge value for delta G. We'll see this as we do more calculations, but thousands of kilojoules is a very large delta G, a very favorable reaction. So absolutely, this would be a spontaneous reaction. Okay? So, any chemical reaction that you can dream up, as long as you can find your reactants and your products on our constants page here, you can predict whether or not that reaction will happen spontaneously. Because these delta G and delta H and entropy values, they're these state functions. So it doesn't really matter that these were tabulated for reactions that aren't your particular reaction. You can still use them and sum them up for your particular reaction. So again, as long as you can find all of your compounds on this table here, you can predict those thermodynamic variables. All right? Now, importantly, if we zoom in here, this delta G has this little circle up here, okay? So really what we calculated here is our delta G with this little circle, what we call delta G naught for this reaction here. This little circle means at standard state. All right, standard state is a specific set of conditions. Okay, in particular, it's a temperature of 298 Kelvin. All right, so this delta G value that we just got here, it was a particular temperature here. The delta G will depend on temperature, as we saw in our equation. Right? So those values that you calculate here, they tell you whether or not a reaction is spontaneous at a specific temperature. Okay, so I know that this reaction is very spontaneous at 298 Kelvin, which just by the way is 25 degrees Celsius or room temperature. Right? So this reaction will occur at room temperatures. Okay, so if we want to know whether our reaction is spontaneous at room temperatures, great. We're just going to use this delta G column here and calculate what that free energy is. Okay? If we want to use any other temperature, we're going to have to calculate the delta H and the entropy and instead use our formula, delta G equals delta H minus T delta S. So at any other temperature, we must use this formula here. All right, turns out that the value of delta G is very sensitive to temperature. Truthfully, entropy and enthalpy, they do change slightly with temperature, but you can get a really good idea of just using the values at standard state and then using this equation here. All right, so let's pick another example equation here and do this from scratch. Two nitrogen dioxides forming dinitrogen tetraoxide here. Okay, so let's go to our table, grab these values. They're going to be listed under nitrogen. Okay, I got nitrogen dioxide gas. So that's one. It's my reactant. And I have my other reactant. Not my reactant, my product. Okay, so I want you all to do this on your own. Is this reaction spontaneous at 298 Kelvin, at room temperature? Okay, so using these thermodynamic values here, again, the first column's delta H, then delta G, then entropy. All right, take a moment and see if you can't tell me whether or not this reaction is spontaneous or non-spontaneous at room temperature. So my delta G for my, I guess specifically my delta G naught, the at 298, it's going to be my products, delta G, my 99.8, minus my reactant times that stoichiometric coefficient. Right, so minus 2 times the 51.3, I get a delta G of negative 2.8, and again, those units are kilojoules per mole. So is this reaction spontaneous at room temperature? Yeah, I have a negative delta G. right, but now let's say I want to know if it's spontaneous at 400 Kelvin. Now we're going to have to use our other values. We're going to have to use the equation. Delta G is delta H minus T delta S. And we're going to have to use our constants page to calculate what that delta H and delta S are. Okay, so everybody take a second and give me delta H and delta S based on these values here. Same way, products minus reactants times their stoichiometric coefficients, same way we did delta G, just using the columns for delta H and S. All right, and actually before we go on, let's just look at this chemical equation carefully. Do we think this reaction will be entropically favorable or entropically unfavorable? Unfavorable, right? I have two gas molecules combining into just one. That is creating order. So this would be, we would predict that this would be entropically unfavorable. All right, so let's see if that shakes out in our calculations here as well. That is not something that we can get just by looking at it. It's because you have two gas molecules that are combining into just one, right? So that is intrinsically creating order. You got two things floating around. Now you just have one. That's a more ordered state to just have the one gas molecule. So my calculations here for my delta S, again, you're going to take your products minus your reactants, but then because in my balanced chemical equation, I have that stoichiometric coefficient of 2 out front of my reactants, I'm going to take those values and multiply them by 2 in my calculation. Okay? And so indeed, we get a negative delta S, right? So this would be entropically unfavorable. Right? Positive delta S is good, negative delta S is bad. Okay, but is this reaction endothermic or exothermic? If I look at the value of my delta H here, is that exothermic or endothermic? Exothermic. Right, so we see we have this push-pull going on. From an enthalpy standpoint, it's favorable, it's exothermic. But from an entropy standpoint, it is unfavorable, right? right? It is entropically unfavorable. So now we're going to crank the temperature up here to 400 degrees, and we want to see if this reaction still occurs spontaneously. The one thing we got to be careful and pay attention to here are our units. If we go back to our table, enthalpy, much like our delta G's, are listed in kilojoules per mole, okay? But entropies are only in joules per mole Kelvin. All right, so we got to square away those units before we can add these things up. Okay, so again, let's just be good and put our units in. This is kilojoules per mole, but this is now joules per mole. It's also got Kelvin in the units because that will cancel out when I multiply it by my temperature. All right, so let me just real quick do this conversion here. Oops, this is joules per mole Kelvin. I'm going to use the fact that there are 1,000 joules in 1 kilojoule. All right, so what I'm going to use in my equation is negative 0.1758. because now my units are all squared away. Kilojoules per mole Kelvin. All right, so now I'm ready to plug everything into my equation here. I'm going to take that delta H value. I'm going to subtract my 400 Kelvin times that point, or rather the negative 0.1758. And actually, let me be good with my units here. This is kilojoules per mole. This is Kelvin. And this is kilojoules per mole Kelvin. All right, bottom line here, I do my delta G calculations. Now I get positive 13.08 kilojoules per mole. So is this reaction spontaneous at this higher temperature? No, this would be non-spontaneous. Okay? And that's because it is entropically unfavorable even though it's exothermic. So what we had laid out at the beginning, I mean, this checks out if you look at our little chart that we created, right? For a reaction that is exothermic but entropically unfavorable, we would expect it to be non-spontaneous at high temperatures, right? So as I increase the temperature, I finally cross some threshold where this reaction is no longer going to be spontaneous. Cool. All right, we'll pick up with all that next time. All right, so let's get started. We're going to finish up our discussion of Chapter 19 today, thermodynamics. Just kind of to review what we did this week. We started this week by introducing these thermodynamic terms, the one that you already went over last semester, enthalpy, as well as this new one, entropy, and how those are two key components in this third one, free energy, which tells us whether or not a reaction will occur spontaneously, right? And then we said that these quantities are actually super useful because they're what are called state functions. They are path independent, which means that their value depends only on where we start and where we finish in a chemical reaction. So what our reactants are and what our products are. If we know those two things, we can figure out what our delta G, delta H, and delta S are for these reactions. All right, so then we used our constants page. Our constants page, we pulled that data off of there for each of these components. And so for a given chemical reaction, we could calculate, using this tabulated delta G values, the delta G of that reaction. All right, and if you can find your reactants and your products on that table, you can do this for any reaction that you can think of. All right, so for this particular reaction, we found that it was spontaneous. Delta G was negative. All right, but importantly, what we solved for was delta G naught. And that naught means something special. By the naught, I mean the little circle on the delta G. Okay, we call that delta G naught. That circle meant something very specific, and that was that that value was tabulated for this reaction at standard state. All right, and standard state, we said, means that we have a specific temperature, a temperature of 298 Kelvin. Okay, we're going to add on to this standard state business a little bit today. So this is an important caveat to keep in mind about these quantities. So we got our delta G at standard state, at 298. And again, we found this reaction was spontaneous. But then we said, all right, well, what happens if we increase the temperature? Delta G is very sensitive to temperature. So instead, we have to use this equation here, right? Where we tabulate the delta H's and the delta S's and use that to calculate delta G, right? So that's what we have to do if we're at any other temperature outside of standard state, okay? And so that's kind of where we left things off. We're just going to build off this. Basically, at the beginning of the week, we sort of built our toolbox of thermodynamics up, and now we're going to put those tools to use, right, to explain chemical reactions. So now we're going to take a look at another reaction, or actually what would be more correctly described as a phase change. So we're going to look at liquid water going into the gas phase, a process we would call boiling. All right, so this isn't so much a chemical reaction where bonds are being made and broken. This is a phase change going from the liquid state to the gaseous state. Okay? Nonetheless, we can tabulate all of those good things that we learned how to do. We can ask, is this reaction, or I guess, again, should be more correct, phase change, spontaneous at 298 K? All right, so if I'm talking about spontaneous, not spontaneous, which one of those three thermodynamic values do I care about? Enthalpy, entropy, or free energy? Free energy, right? That tells us whether or not the reaction occurs. So spontaneity, I'm talking about free energy. So let's go to our constants page. And we're going to look up these values for water in the liquid phase and water in the gaseous phase. I believe these are actually listed under oxygen. Yeah, here we go. All right, so I just grabbed these values from the table. That first column is the delta H, then the delta G, and then the entropy. Okay, so everybody take a second and tell me whether or not this reaction is spontaneous, or phase change, is spontaneous at 298 K. right, remember our delta G for this reaction is going to be products minus reactants, right? That's what we want to chant to ourselves. Similar to when we were doing equilibrium constants, we were like products over reactants. When we're doing these thermodynamic values, products minus reactants, that's what you want to have in mind. All right, and in particular, the products multiplied by their stoichiometric coefficient minus the reactants multiplied by their stoichiometric coefficient. In this case, it's 1 to 1, but just keep that in mind. Okay, so the delta G naught for this reaction, I'm going to take my product, which is the gaseous water. So that'd be that value there, the negative 228. And I'm going to subtract the reactant side, the negative 237.1. And I get positive 8.5. And the units on our table here are kilojoules per mole. All right, so using those thermodynamic constants, I can predict whether or not this reaction is spontaneous or non-spontaneous. For this reaction here, what do we got? Spontaneous or non-spontaneous? Positive means non-spontaneous. All right, and so you can do this for any phase change if you can find those two values on your table here. For this particular compound, we have some experience. I think we all know water, right? And so does this check out? Does water spontaneously boil at room temperature at 25 degrees Celsius? No, so that kind of checks out, right? So again, we can do this for any compound, whether we know or not. Look it up on our table here. Water, we have an intuitive sense of. Okay, so now let's ask ourselves, is this phase change spontaneous? At 400 Kelvin. All right, now let's remember Kelvin equals degrees Celsius plus that magic number, that 273. So if I wanted to convert this from Kelvin to Celsius, because I think we have a little bit more intuitive sense about Celsius, that would be 127 degrees Celsius. All right? So intuitively, do we expect that water should boil at 127 degrees Celsius? Cool. So we should get a spontaneous reaction here. But again, let's just go through it. Now that I'm no longer at my standard state temperature, I'm going to have to calculate the delta H and delta S values and use that equation for delta G to get to this particular value. All right, so everybody take a second, calculate the delta H and the delta S of this reaction. Whoa. And actually, real quick, before we get our values, just looking at this chemical equation here, would we expect this to be a entropically favorable or unfavorable reaction? Going from a liquid to a gas, entropically favorable or unfavorable? Favorable, right? Going to that more disordered state. More favorable implies a positive delta S, right? So let's see if we get a positive delta S here. Entropically favorable. All right, and listen, this is a little bit more difficult, but important that you guys can still see here is whether or not this reaction would be exothermic or endothermic. All right, I think it's a little easy to spy that it is an entropically favorable reaction, but is it exothermic or endothermic? Are these liquid water molecules going to have to absorb heat to get to the gas phase or release heat to get to the gas phase? They're going to have to absorb, right? So that would be an endothermic reaction. All right, so let's see if that pans out with the values that we get for our delta H and delta S here. right, so we get our delta H and our delta S using those values from our table. And indeed, we see that we have an endothermic reaction that is entropically favorable. All right, so that checks out. Now, one thing, and I got these units from that table as well, one thing that we really got to keep in mind here is our units for delta H and delta S are different from our table, right? So I'm just going to go ahead and convert this from joules Kelvin mole into kilojoules Kelvin mole by dividing by 1,000. Now my units are squared away and I can use that equation. All right, so delta G is going to be equal to the enthalpy minus temperature times the entropy. Plugging in the values that we got here. Negative 3.52 kilojoules per mole. All right, so according to our delta G, does that check out? Spontaneous or non-spontaneous? Checks out, right? So this is spontaneous. Okay, so there's one more cool thing that we can do with these phase changes in particular here. All right. The temperature at which water turns from a liquid to a gas, we call the boiling point. Or T-boil. All right? So this temperature, what does it mean to be at T-boil, to be at the boiling temperature? At that temperature, there is this perfectly balanced equilibrium between the gas and the liquid phase. All right, that's what it means to be at that boiling point. So this phase change is at equilibrium. And it turns out that at equilibrium, the delta G for a reaction will equal 0. All right, so we can use this fact right here that delta G is 0 at equilibrium, which is the temperature at which this boils, to predict what that boiling temperature is going to be. Because if we look at our equation here, we have our delta H and our delta S from our table, right? Check, check. We got those values. I know that at equilibrium, this delta G is 0. So then what's the only missing variable from my equation here? My temperature. So I can figure out what that temperature is, that this is going to be at equilibrium, again, what we call the boiling temperature. All right, so the last thing we're going to do here is predict that boiling temperature using this equation. Everybody take this equation real quick. Substitute in 0 for delta G, and then rearrange it to solve for the temperature, right? Do a little algebra and solve that equation for temperature when delta G is 0. What you would have done if you would have rearranged it that way is you would have gotten negatives on both sides and they would cancel each other out. Okay. Right? Both sides would be multiplied by -1. So yeah, I could take this side, multiply it by -1, and that makes them both positive. Okay, so we get that our temperature is going to be equal to that enthalpy value from our table divided by the entropy value. All right, let's just keep in mind, again, units, we're going to have to make sure our units square away, so we're going to have to use our delta S value in kilojoules per mole Kelvin. And I'll be good about units here just so we can see what's going to happen. Kilojoules per mole. Okay, so we get 370.4. If we look at our units, kilojoules will cancel out, moles will cancel out, and I'm left with 1 over Kelvin, which is the same thing as Kelvin. So my temperature units here are in Kelvin. And again, we probably don't have a real good intuitive sense of what a temperature in Kelvin is, so let's just convert that to Celsius real quick. Again, subtracting that magic number, we get 97.4 degrees Celsius. Okay? Now, well, again, we all have a good intuitive sense of water here. What is the boiling point of water? 100 degrees Celsius, okay? So we got a good approximation here because, again, in truth, these values of delta H and delta S also depend on temperature a little, and what's listed is only their values at standard state. But again, they don't change that much, so we can get a really good approximation of their value at different temperatures. And again, what are we, like 2.5 degrees off? That's not too bad, right? So if we can use this big book of tabulated values to get very close to what our boiling temperature is, great, okay? To be clear, you can also do this for melting points as well, for the solid to liquid phase change. Again, same logic. At that temperature, the delta G is going to be 0, so we can rearrange that equation to solve for that melting temperature. All right, so there's one last cool thing that we're going to go over here for our thermodynamics. Everybody contain your excitement.